Okay, good morning to or good afternoon to you, depending on wherever you are in the world, and welcome to this webinar presented by the Water Resources Authority in conjunction with the International Atomic Energy Agency, focused on stable isotopes in precipitation in Jamaica and the surrounding regions. This is one of two webinars where the follow-up will be on Wednesday, the 16th of March, looking at the relation of the stable isotopes in water in the Rio Bueno sub-W. But today we're going to be looking at precipitation, and this is a part of the IAEA Joint WRA project, JAM 7006, looking at the flow dynamics in the Rio Bueno sub-W in Jamaica, the karstic Rio Bueno. Our presenter today is Dr. Aurel Persoy, who is from Romania. And without further ado, I will turn over to him in doing this presentation. Dr. Persoy, over to you.
Thank you very much. Thank you, Geoffrey, for the nice introduction. Thank you, everyone, for attending. I'm glad to see you this early there, late afternoon here already. So I think I recognize some of the names. So I'm happy to see you again. And I am happy to talk to you today about the stable isotopes in precipitation in the wider area around Jamaica. And this would be mostly like an introductory presentation for the next presentation, which will be on Wednesday, as Geoffrey said. And this will be about the data that the Water Resources Authority already collected from Jamaica, from the Rio Bueno catchment area, spring data, river data, the wells, and so today's presentation is going to be mostly like a general introduction on the stable isotopes in precipitation as the main source of water feeding the karst system or karst systems in the Rio Bueno area. So I will share my screen. Let's see if it works, and then I will continue in a minute. Share screen, there it is. Okay, how share screen? Yes. There. So I believe it is now visible. Let me just try to minimize this thing. Okay, this I need to minimize. This I will not need. Okay, so if someone can quickly confirm that my screen is visible.
Your screen is visible. We're seeing it fine.
Okay, thank you. And okay, let me just stop sharing for a second because I use Keynote and I cannot see my mouse moving. So I will save it as a PDF and I will open it again. So just a second, please. Okay, I will try again. I couldn't see my mouse, my pointer, so that's something that I will need. And hence, okay, so let's do it again. Share screen, here it is. Should be visible now, full screen, and also now I can see my mouse moving on the screen. I hope you see it too. So yes, the title is Stable Isotopes in Precipitation in Jamaica and surrounding regions. It's let's see. Okay, so I will be talking a bit about stable isotopes in precipitation, and because I am not sure that everybody was present at the previous talk, I would take a step back and just quickly introduce the theory behind using stable isotopes in precipitation and what can they tell us and how to interpret a bit of data. And here you can see I put these two titles, the title of today's presentation and then the titles on Wednesday presentation, and the idea being that the aim of this one of the aims of this study that the Water Resources Authority in Jamaica is doing is to use stable isotopes in water to track the processes linking the atmospheric processes, you see it up here, with the processes on the surface and processes underground. So basically there is stable isotopes in precipitation, and then once they got into the ground, onto the ground, before getting underground, there is a series of processes happening at the surface. Evaporation, the infiltration rate can change in time, and then we have karst processes inside the karst system. And all these three groups of processes are ultimately influencing the output from the karst, and that is the springs that are being used for human consumption and agriculture and industry and so on. So basically, if we want to understand where is the water coming from, how much water is coming, how much of this water is available now, how much is going to be available in the future in different climate scenarios, we need to understand the links between modern day climate and weathers and the stable isotopes in precipitation. Today, I will be talking on this part, number one here, isotopes in precipitation, and tomorrow and 2 days from now on Wednesday, we'll be discussing mostly on the data that has already been gathered and generated by the Water Resources Authority from the karst area and the Bueno area, Rio Bueno catchment. Okay, so here is the brief outline of today's presentation, the introduction, a few words about the general stable isotope geochemistry, then oxygen and hydrogen stable isotopes in precipitation, and then the floor will be yours for discussions and questions. I will not end today's presentation with conclusions or like take-home messages, let's say so, but I would prefer to do this on Wednesday after we look at the other data. Nevertheless, you will see that there are some messages that I think it's important and would like to take as the conclusions, let's say, of today's talk. So let's go to the introduction. Here is just a general chart that I took from a paper by Siaki et al. Published a few years ago. So general idea of a watershed, you see precipitation and then surface flow and underground flow and all the processes that are, not those general processes that are happening as the water moves from the surface on the ground and underground, and the different type of isotopes that can be used to investigate different types of processes. And mostly because the analysis that we are doing are oxygen and hydrogen isotopes, you will see that most of the information here is based on these isotopes, but also there is other different types of isotopes that can be used, very useful. And especially in the karst area, here is the carbon isotopes in the carbon isotopes in both the organic matter and in the inorganic dissolved inorganic carbon, dissolved organic carbon. So the carbon pools that can be found in limestone areas, karst areas. And these are important because by combining oxygen, hydrogen isotopes in water and carbon isotopes in the different species of carbonates and carbon that we can find in karst, we can understand the rate of the processes and the dynamics of the processes, and also what kind of processes are happening. For instance, whether we have a precipitation of calcite in case, or we have dissolution. And then these are important for both the carbon budget and the water budget in the area. And here is a chart that only reflects generally what is happening with isotopes, oxygen and hydrogen only in precipitation. And you can see the general circulation. So it all starts from the ocean as the main source of water through evaporation. And then we have rain out processes as a cloud is moving towards the continent, towards inland. We will have a continuous rain out. So for instance, if we start with a delta O18 of 0, which is the mean for the ocean, for the global ocean, evaporation will result in the delta O18 of the moisture, which is lower than that of the ocean. So we start from 0, the vapor will have around minus 14. This is just a number to get an idea. So it will be depleted in heavy isotopes. And as we move further inland, the precipitation will be enriched in heavy isotopes, and the second precipitation will be more depleted than the first one, and so on. Now, these are processes in the atmosphere. as we move on the surface, we have surface runoff, we have underground runoff, and it is not just a simple model from continent to the ocean and back to the continent, but we can have a excursion, let's call them, where the water is going through a lake or a river or just underground and is going to several other types of processes like evaporation. So this, we have the large cycle between the ocean and the continent, and we can have a smaller cycle between continents, evaporation on the continent and reprecipitation. And this is a very important cycle because it turns out that in many cases, the source of the moisture that is feeding local precipitation is evaporation from water bodies that are not the main ocean, but they are local lakes or even standing water on the ground, or even water evaporating from the ground. For instance, if you have water in the soil and you have a very dry and hot season, that water will re-evaporate and precipitate and re-evaporate again. So this whole cycle will happen on the continent without being necessarily linked to the ocean. And from this local image, I will switch to this global image. And I'm showing this because what is happening in a given area, like here, for instance, in this case here in Jamaica, is not something that is only local or regional, but is part of the global circulation, atmospheric circulation. And it's not that water that is being fed to precipitation events in Jamaica is coming from the polar areas. That's not what it means, but that the climate in different parts of the globe are affecting what is happening in are changing the circulation patterns in the region, and these are in turn affecting the stable isotope composition of precipitation. So it is very important to understand. So if we understand how global atmospheric circulation is happening, we also need to understand how the isotopic composition of the precipitation is changing in relation to these global types of circulation, so like the Hadley cell or the influence of the trade winds and the change between the trade winds, and so. So this is just to emphasize the importance of putting this into a wider complex, into a regional complex, and further into a global context. And just to emphasize why this is important, this is a slide that I previously showed. This study shows the future change in precipitation, and you can see it's rather patchy at a global scale. So you can have theoretically global circulation models are telling us that in the future we will have areas that will become drier in brown, and areas that will become wetter in blue. And important it is that we will have areas that will become drier but more variable in green, and areas that will become drier and less variable in brown. And this is very important because it's not only the fact that they will become drier, as you see here with green and brown, but it's also important the variability, because this is especially important if you consider when is actually raining and when is the groundwater recharge. If you have an area that is extremely variable, then you can have precipitation both throughout the entire year. And depending on when recharge is happening, this could be a good thing or a bad thing. Or the other way, you can have a very low variability in the precipitation. And if this happens in a period when it's also very warm, you may result in a climate that will not favor the infiltration of water and recharge of the groundwater. And the problem is that if you look at where Jamaica is located on this map, so this is only one model, it's not like a proof that it will exactly happen like this, but it's quite good. Jamaica is somewhere in the limit between drier but more variable and drier and less variable. So it is not yet sure what will happen in terms of precipitation variability in the region. It seems that it's going to be drier, but again, you can see that the limit between this dry, so the brown and green, both indicating dry, and the wetter, which is indicated by blue, is somewhere in the vicinity. And these are global models, so there is an error associated also with the limit of these domains. So it could be very well that the entire region will become wetter in the future. regardless of what scenario are we in, whether it's becoming wetter or drier or more variable or less variable, we need to prepare for this. And in order to prepare, we need to understand what is happening in the present. Because if we not know in the present what are the processes behind precipitation variability, and we know which are the processes between the recharge patterns of groundwater related to precipitation, we can better prepare for these scenarios, whatever these scenarios are in the future. So this would be a very important motivation for this study. And if you think, for instance, like how is weather changing from one year to the other, you see that there is a huge variability on a yearly basis. And in terms of precipitation amount and in terms of temperature, air temperature changes. And the same kind of variability translates also to the stabilized composition of precipitation. So if we are to understand how the air temperature is changing, then the longer the time series that we are having, the better it is. The same is for precipitation amount. We cannot say that we understand the precipitation changing in an area if we measure for 1 year or so. And then it's the same for stable isotopes. We need a longer time series just to understand for different types of weather what is happening with the stable isotopes in precipitation, and then how further these are transferred to the underground. Okay, so I will now quickly walk you through a stable isotope geochemistry, a bit of theory. So I apologize for those who know these things very well. If it's too much, just please stop me. I will quickly walk through you. So here it is, very briefly, we are talking about oxygen and hydrogen isotopes. So the important thing to have in mind is the fact that the ratio, what we are measuring when we are talking about the delta O18 is the ratio of heavy to light isotopes of hydrogen, or the ratio of heavy to light isotopes in oxygen compared to a standard. So is this ratio between the heavy and light isotopes of either hydrogen or oxygen. And just here quickly, so we have for hydrogen, we can have 1 proton, which is hydrogen 1, and the deuterium has 1 proton and 1 neutron. So the mass is already twice, the mass of hydrogen 2 is twice the mass of hydrogen 1, and oxygen is a mass of 18 compared with a mass of 16. And this is extremely important because depending on the mass we have the energy, the potential energy, the dissociation energy between the atoms. So if we have the link, for instance, if we have a molecule of water that is composed of hydrogen 1 only, then the potential energy between the 2 bonds, hydrogen, is less than that between hydrogen and deuterium, you see here, and which is less than that between deuterium and deuterium. So that means that we need more energy to break a molecule of water that is composed of the heavy isotopes than we need to break a molecule that is composed of light isotopes or lighter isotopes generally. So the more heavy isotopes we have, the stronger the bonds are, and the more energy is required to break this one. So the bottom line is that these strengths are higher for heavy isotopes. And because these bonds, the strength of the bond is higher for the heavy isotopes, that means that the amount of energy that is required to dissociate a molecule is higher. So that means that it's easier to break a molecule that has light isotopes only, or that has more light isotopes, than it is to break a molecule that has more heavy isotopes. And here is the result very, very quickly. So if you have water that, regardless what water body, that has both light isotopes and heavy isotopes, the molecules that have more light isotopes will evaporate slightly easier. And this is because it has more light isotopes. That means that the strength of the bonds is smaller, so it will be easier to break the barrier between water and vapor and evaporate. However, once the water gets in the atmosphere, in order to have rain, we will need condensation, and condensation will work the other way around. So the molecules that have the heavier isotopes will preferentially bond together to form liquid water, and that will rain out. So when we have evaporation, then it results that the vapor is enriched in the light isotopes, compared with the water, and we have precipitation is the other way around. Precipitation is enriched in the heavy isotopes compared to vapor. Okay, and here is the result. You see the delta O18 of the vapor is enriched in heavy isotopes, in light isotopes. That's why the value is more negative. It starts with 0, and the value of the vapor is -12. Now, the rain compared with the vapor will be enriched in the heavy isotopes. So this delta O18 will increase compared in precipitation, will increase compared with the vapor. But because we have this rain out, this distillation of the water, we will remove preferentially the heavy isotopes, oxygen 18 and hydrogen 2, so that the remaining moisture, here the vapor, will be even further depleted. You see this value of -15 compared with the value of -12. Consequently, the next rain will be further depleted. So this is the second rain, which is -11 compared to -3, leaving the remaining water even further depleted in heavy isotopes, and so on and so on. So this process continues until all the water is theoretically removed from the cloud. Now, compared to this simple model, think about the possibility that we have evaporation, rain out, and then here on the continent, we have some further evaporation, so that this cloud here is not only left with water that came from the ocean, but is a mixture of water that came from the ocean and water that was evaporated from the continent. And then this one can also be a sum of moisture coming from the ocean, moisture evaporated from here, and further moisture evaporated from here. So it's a very complex history. It's not as simple as here, but if we understand what is happening what the physics behind the rain and precipitation and the evaporation, then we can add isotopes on top of it, and we can combine this and get a better understanding of the end rain. So if you're interested in the rain here, in this area, or this area, or this area, then by combining all the processes behind what is registered in this area, we can get an understanding of where exactly the moisture that is raining here coming from. Is it from here, or from here? So this is why it is important to understand what is happening in this rain at our study area, supposedly if it's here, in order to understand how further this is transported into the underground. Okay, so because of this rain out, this is I'm showing just the theory behind the result of this theory, and you can see that there is a fairly good distribution of this is hydrogen isotopes of delta D or delta 2H in precipitation globally, which is related to the change in temperature. You can see that areas that are closer to the equator have higher values, whereas areas that are further from the equator, like here in the northern or in the Arctic or in the Antarctic, have lower values. The same is true if we move from the ocean towards the continent. As we move further in, there is this continuous rain out with precipitation in the inner part of continents being depleted in the heavy isotopes. Again, another point that can be seen here is the influence of the high mountains. We've seen here the Tibetan Plateau, or we can see here along the Andes in the South America. So these are forcing the moisture to move upwards, like here. So there is this continuous rain out as we move from the ocean towards the continent, or as we move from lower altitudes towards higher altitudes, or as we move from lower latitudes towards higher latitudes. So a theoretical distribution would look like this. But while this is very good for, let's say, teaching purposes, there is numerous local influences that are completely changing this picture. So if you are looking at a specific area, we can have different processes that are affecting the stabilized composition of precipitation at that site, and are muddying this very nice general picture. Now, why is this important? Theoretically, we could sum all the data that we have and then come up with this kind of methods, thinking, okay, we understood what is happening. And because we can link it to climate. This is the present day temperature distribution, and the present day distribution of stable isotopes in precipitation is following that of temperature. However, if we look at what has happened in the past and what will happen in the future, you see that climate is not steady. And because we have this very strong link between climate and stable isotopes in precipitation, that means that the stable isotopes in precipitation will also change, are changing in time and will change. So compared with the natural one, we have this continuous warming in the present. So it is expected that the delta weighting of precipitation will react to this change in climate and will also change in the future. And then we need to understand what is happening in the present in order to prepare for this future changes. And here are a bit just a summary image of what can be done with if you understand the distribution of stable isotopes in precipitation. So if we plot oxygen versus hydrogen, there is numerous processes that can be understood. For instance, whether the moisture is coming from colder areas or warmer areas, which is the source of the moisture? Is it an arid source? Is it a humid source? And if we can understand the source of the moisture, then it's easier to understand if we have model data, what will happen in the future. And if we have the delta weighting of precipitation, then we can understand what is happening in the surface waters like rivers, reservoirs, lakes, groundwater, and so on. But in order to understand all these processes, we need to understand what is happening in a precipitation. And just again, to further emphasize this, I'm showing here for the Caribbean. Maybe the base map is not very clear, but this is North America here. Here it is South America. And Jamaica would be here. So these are 7 types of circulations that are specific for the Caribbean. And you can see that the source of the direction of the winds is changing. So it's not as simple as one might assume. So we can have different types of circulation, and all these types of circulation are resulting in the moisture being advected from different sources. And because the moisture is coming from different sources, and that means that it's also variable in terms of amount. So we can have a moisture source that is from the ocean, or a source that is mostly from the continent, or a source that is from a warmer or a colder area. And on top of these information, these types of circulation, it is very useful to have stable isotope values, because then we can track how these are from precipitation, what are the sources. And then if we have stable isotopes in precipitation, and at the same time we have stable isotopes in groundwater or springs or rivers, we can link these values in rivers and springs to the source of moisture, like saying that, okay, if we have rain coming from this direction, then we have higher amounts, and then we can have a better recharge or lower recharge, and so on. So this is the rationale behind using this kind of analysis. And I would like a bit now to talk on oxygen and hydrogen isotopes in precipitation in the Caribbean. I will use some data that has been available from the GNIP database. And what I will mostly discuss will be how an area how different are the values, and how can they be used, or why it is important to have as much data as possible in order to understand what we have in terms of water resources. So I will start with this plot. This is the data that has been collected by the Water Resources Administration Authority in Jamaica. Very quickly, the black line, the thicker line, shows the global meteoric water line, which is the relation between the delta O18 of precipitation and delta 2H of precipitation at a global scale. And the thin black line indicates the similar relationship between delta O18 in precipitation, delta 2H in precipitation in Jamaica. Now, this is only for illustrative purposes, because it's based on 7 data points collected between March and September. So it is not representative for the whole year. Okay, it's only for half year. So it's like measuring temperature for half a year only. So this is not at this point, it is not correct. But I just put it here for illustrative purposes. And if you look at this line, it is above the global meteoric waterline and somehow parallel to it. Now, this will give us just a very quick information. If we go back to this, this line, you see this line here, which is parallel to the global. The black line is the general global, and a shift of a line of the local precipitation to the left of the global one will indicate that the moisture resulting in that precipitation is mostly coming from an arid source. Now, arid source is a bit strange thing to say, but what it means is that very likely the moisture that resulted in precipitation in Jamaica in 2021 between March and September was coming from an area that was warm during that time. So an area that was warm, like strongly evaporated surface. But this is only half year of data, so it is not extremely sure to say about this. Is indicated by these black dots here. So you see that most of the dots are somewhere in this region, the black dots. And what is interesting is that the red crosses are the values of precipitation collected during the tropical storm Grace that hit Jamaica last August. And you can see that the water of this tropical storm is completely different than the remaining water collected since between March and September. And there is one data point down here of precipitation, and this data point here is the August precipitation. And you see that compared with the previous year, with the data between March and September, precipitation in August was down here, so very depleted, likely because the influence of this one single tropical storm. Now, tropical storms do not hit Jamaica every year regularly. So you see, if we want to look at the delta O18 of delta stabilized composition of precipitation in Jamaica in 2021, and we make an average of all these black dots, these will be strongly influenced by this one single tropical storm. Maybe next year, maybe this year in 2022, there will be no tropical storms, so it is expected the value will be not that depleted as this one. We don't know, but it just shows how important it is to get water throughout several years and to understand how one single event is affecting this, the values on an annual basis. The color dots are from rivers, from sinks, springs, and wells. And I will mostly discuss them on Wednesday. I just put them here for illustrative purposes, just to get an idea of how we can use this data. And here the inset shows the average values. And you see black is precipitation, yellow is sinks, rivers are indicated by blue, and then springs by brown, and the green indicates the wells, the deep wells. Now, these values are different from precipitation. And this is also because we have only summer precipitation. So we don't have data from precipitation that was falling between September and March. So very likely it's possible that the fact that we have the rivers down here is because some of their waters are coming from either a different region or from winter recharge. And you can see again that the sinks have higher values, likely reflecting or possibly reflecting evaporation of the water after precipitation. And the deep wells and the springs have the closest values, likely indicating the possibility that they were underground and more conservative to changes. We will see a bit more into detail on Wednesday, but we will need more data on precipitation to understand what is happening. So this is the data from Jamaica, and I will take a step to enlarge the study area. So I took some data from Honduras and San Salvador, Dominican Republic, Puerto Rico, and Cuba here in Havana. And you can see that this is the data these are the stations. There are some further stations in the US, and there is in Mexico and in South America. But you can see how important is the location of Jamaica and how important is the work that the Water Resources Authority is doing there by collecting these samples. Just by filling in the gap between these stations, in the east, this north, this west. So it's right in the middle. So there is this huge unknown area in the middle, and Jamaica is perfectly placed, and this study is perfectly placed there to fill in the gaps. So if you want to track precipitation that is coming from east or from north, we have this in the middle, and this data can offer us a lot of information, hopefully. So here is a bit on the data. I plotted again here the hydrogen versus oxygen for several stations. Havana, you can see the color codes are the same. So what you see here in blue corresponds to blue here. So you see that the values are almost similar, close enough, because we are in the same region, but there is a bit of variability between these. I think the most important is El Jarral in Honduras, which is the furthest from it. And these are the meteoric water lines. So you see there is a huge spread between the values, especially between the intercept. And this is very important, especially when we are discussing this, what is happening with the surface waters. So yes, I plotted here the data from Jamaica here, but this is data only for a few months. So likely the values from this fall and from this spring will plot somewhere here, and the value of this slope will radically change once we have the whole data set. But okay, where does it? Yes. So here, this is the same. So here is the whole data set. What I did in the next slide, I removed the data points. I only left the lines, and I zoomed in on this part so that it will be better visible what I want to say. So here it is, the same line, the same colors. The thick black line is the global meteoric water line. So this shows, this is the average value for several hundreds of stations over several tens of years over the entire globe. And what you can see that locally, there is an important divergence between the sites. So for instance, how can you use to understand? You see this line here, El Jarral in Honduras, is almost parallel to the global one, but is shifted further to the left. That likely indicates that some of the moisture, or an important part of the moisture that is feeding El Jarral in Honduras, is coming from an arid source, like here. Whether this is a continental source, like from northern part, let's say precipitation coming from continental sources in Mexico, it's up to debate. It's not yet very sure. These lines, if we are to think in terms of precipitation only, we could say that they are not very different from each other. However, when we are talking about water resources, the slope of these lines become extremely important. And this is because generally, let's say if I have it here, yes. What is, if you look here, river surface waters, whether it is rivers or lakes or groundwater before infiltration further down, they will go through evaporative loss. So if we measure waters from surface, if we measure surface waters, these will, depending on how warm it is or how warm and dry it is, the atmosphere, they will go through a certain amount of evaporation. And in order to quantify evaporation, we need to put it in the context of this meteoric water line. So here it's general data from lakes, and you see that all lakes in all climates are shifted from the global meteoric water line. And this is varied also for tropical areas, for arid areas, temperate, and so on. All of them are on this evaporative trend. And if we want to understand how much water we lose to evaporation, when we lose it, we need to be able to measure the distance between a line. So if we have samples from surface water, they will plot on this line. But in order to estimate how much is lost to evaporation using stable isotopes, we need to have this the local meteoric water line. And depending on the slope of the local meteoric water line, we can estimate how far these waters are from the meteoric water line, and then we can understand how much evaporation they went through. And then two lines, so we have this blue line here and the green line there, we would say that, okay, they are close enough, but because of this difference in slopes, we can get completely different results when we have river data and surface waters generally, and we want to compare with the precipitation. So this is maybe the most important application that I see of calculating local meteoric water lines and trying to estimate or trying to understand what is happening with surface waters in relation with precipitation. And then here it is again. So this is for all the stations in the Caribbean. And here I also put it for the samples from Jamaica. So you see, depending on, I plotted these lines, the local lines, not the ones from Jamaica, but the ones that from the wider area, so from Dominican Republic and Havana and so. And you can see that, for instance, we can say that, okay, if we use this line, basically these the waters that are sinking, that they had no evaporation at all. So basically, all the water that is sinking is not evaporated. However, if we compare these orange dots that are sinking rivers with the local meteoric water line from, I think green is Havana, then we can say, yes, they are evaporated. And if we compare with the blue one, which is the Dominican Republic, they're even further evaporated. So then for this reason, it is very important to have a local water line for Jamaica to understand exactly what is happening with these waters. Are they evaporated or not? Are they mixing or not? Are they coming from summer precipitation? Are they coming from winter precipitation and so on? So this is the importance of having a local line, because without it, we cannot understand what is happening with our waters in the after precipitation. And here is another point for important. You can see two stations. This is Santana and Santana in the Dominican Republic, and here is Havana. So you can see that there is the precipitation amount, how it changes, and you can see this variability of the delta in precipitation. So you would say that they are close enough, at least if I'm speaking from my perspective. In Europe, I would say, okay, climatically, I don't see that much difference between Cuba and Dominican Republic. However, if I am to go into delta 018 of precipitation, they are completely different. This line here with this line here. So then if I want to study the recharge patterns of rivers in the area, it is very important to know if the delta 018 of precipitation follows this curve or if it follows this curve. And this I can do only by monitoring the local sources. So these were the general data for the area, and because we had this wonderful opportunity last year, and I wish to thank Geoffrey again for jumping to my request. So I just simply sent an email asking Geoffrey, would it be possible now that Tropical Storm Grace is coming to collect precipitation every hour for as long as it rains? And he was kind enough to say yes. So in the middle of this tropical storm, he would walk out every hour and collect samples for, I think, 13 hours straight, and to get these data points, these red crosses. So I will be looking now a bit at the stabilized composition of precipitation during tropical storm Grace. These red crosses. So yes, quick image, and here it is the track of this storm. So as it passed through Jamaica and then made landfall twice in Mexico, once in the Yucatan Peninsula and then in the mainland. And this is for August 17 when it was approaching Jamaica as a tropical storm before getting, I think once it gets through Mexico, it became a hurricane by picking up some more moisture from this sea. So here it is, the data. It's been collected for 13 hours. So the blue line and the square on the left shows the evolution of delta 18 in precipitation as it moved in time. So you see the first values were depleted, and then there was a continuous increase reaching maximum values towards the end of the rain, close to zero. At the same time, and mirroring in reverse the increase in the delta 18, there was a continuous decrease in the deuterium excess. And then in order to understand why the delta 18 was increasing and the D excess was decreasing, Geoffrey also provided climate data. And here on the left column, you will see 3 charts with the evolution of delta 018, and on the right, 3 charts with the evolution of D excess. So you can see that delta 018 was increasing, and there was not a very good correlation with air temperature. So there was a slight decrease in air temperature, but the two are not linked very nicely. Even if we can say, yes, the delta 18 was increasing and the temperature was decreasing, there is not a clear correlation between the two. Also, there is not a correlation with the rainfall amount. The delta 018 was increasing and the rainfall was changing. Also, I did not put it here, but I also looked at the rate of rainfall. Again, there was no correlation between the delta 018 of precipitation and the rate of change. And there was increasingly a very good correlation between the delta 018 of precipitation and the air pressure. So yes, I will come to an interpretation a bit further in time. Here is this, again, the deuterium excess, no correlation with air temperature, no correlation with rainfall amount, rainfall rate, pressure, but it was a very, very good correlation with relative humidity. So you see this change in the deuterium excess and mirrored by a similar change in the relative humidity. As the temperature was, as the relative humidity was decreasing, so was the D excess. So it was the correlations were between delta 018 of precipitation and air pressure and the deuterium excess and the relative humidity. And the interpretation so far, it is that basically what was happening with the air pressure was a proxy for the passage of the eye of the tropical storm. So with basically what we were following was the distance from the collection site and the center of the tropical storm. And with the relative humidity, as the relative humidity was decreasing, the air was drier, so and the amount of precipitation at the same time was decreasing. So you see here in red. So there was a decrease in the precipitation amount and a decrease in the relative humidity. So very likely in the final stages of rain, there was a evaporation of the water that was resulting in these lower values of the D excess close to 0. And here is an example from a similar study done by Ricardo Sanchez Murillo in Costa Rica, who was studying Hurricane Otto in 2016. And you can see here the change in the delta 018 and the change in D excess. As in this case, it was as the hurricane was making landfall in Costa Rica, there was this increase in decrease. It says increase, but it was decrease in the deuterium excess. So you see it was going from something like 20 per mil, it was going down to 0 per mil. So you see this trend in D excess, which is similar to the trend in D excess that has been seen here in the case of Tropical Storm Grace. And sorry, the other way. And then there was this change in for delta 018. So likely these are related to the subcloud processes during this very, very strong hurricane. Now, yes, I put it here. What I want to show here further is, again, I'm coming back to this plot. So you see all the precipitation data from the Caribbean. You see the data from Jamaica in red dots here that were collected in precipitation. And then you see the values of Tropical Storm Grace down here. So it is very likely that these, once we will have the whole data for the whole year 2021, then we will, and then hopefully for 2022, then we will be able to compare the two. And if there, and I hope there won't be a tropical storm or hurricane in 2022, not only for isotope work, but also, as a safety. So hopefully we will be able to compare a year with hurricanes with a year without hurricanes, and then we will see that the delta O18 and delta 2H of precipitation are different between the two. And I will be showing you tomorrow how strongly this one single storm impacted the stable isotope composition of groundwaters. And this I will show tomorrow. Here it's the data before the storm. Here is the tropical storm data, and this is the final. I will be discussing tomorrow here the impact of the links before the storm between the stable isotopes in precipitation and the different types of surface and groundwaters collected in the Rio Bueno catchment, and also the impact tropical storm Grace had on the stable isotope composition of surface and groundwaters. So I think I will leave this here. This is the final slide of today. I didn't put, as I said, any conclusions. I will have them on Wednesday when it will be easier to discuss not only the precipitation data, but the surface and groundwater data. So I am done with my discussion. I will be happy to hear your questions and comments and suggestions mostly. So thank you.
Thank you very much, Aurel, for a very engaging and thorough presentation. I was very interested and intrigued by same. So we'll have questions and answers at this time. You can either place your questions in the chat, or you can raise your hand and I will unmute you so you can ask your question. There is a question in the chat right now asking if you could explain what DXS is.
You mean DXS during the tropical storm Grace?
Yeah, because the person actually wants to ask it directly. So Jervian, I'm going to unmute you and you can ask the question more fully if you want.
Hello, good morning.
Good morning.
Good morning.
Thank you for your presentation. It was very detailed and thorough, as Mr. Marshall mentioned. However, I just wanted to have an understanding of the data itself. So I understand isotopes and the difference between the composition in the vapor and the seawater. However, the graph now, you have the isotope for hydrogen as well as for oxygen. So the water line, I'm wondering if it's a ratio that you're trying to establish, and if the water line for the particular country is above or below that ratio, then you can determine, what's happening in terms of precipitation, in terms of the composition in the water bodies, etc. Yes, I just want to have that to be cleared up, as well as what you mentioned the delta oxygen, and then you mentioned DXS. So yes. I don't clearly see the difference either.
Okay. Yes. So let me see here. I will show. So here it is. So the DXS is a derived parameter, and this is it's calculated by combining both the delta O18 and delta 2H of the two, and then it is so very quickly it gives us further information because it's a combination of two, and because delta O8, while both delta O18 and delta 2H are influenced by the same processes, because the different kinetic processes that are happening during evaporation or condensation. So because let's go. Okay. So okay, so if you look at here at the mass, you see the mass of the height of the, so when we measure delta O18, we compare oxygen 18 with oxygen 16. Now you see the mass of 16 is 16, of course, and the mass of 18 is 18. So that if you think in terms of percentages, it's I don't know, maybe something like 12% difference between 16 and 18. Now, if you compare hydrogen and the hydrogen 1 and hydrogen 2, then you see that it's the mass between 1 and 2. And this is already 100% difference between the two. So the change between the 2 and 1 is, so the mass of hydrogen 2 is double the mass of hydrogen 1. Whereas in case of oxygen 18, it's only 12% more. Because of this, the evaporation and the condensation, all these processes that are affecting both isotopes are that have different values. And because of this, we can calculate the so-called deuterium excess value. And this is a derived parameter. And this will give us further information of the processes behind their variability in the precipitation, for instance. And these differences in the deuterium excess between two precipitation samples are most related to what the conditions that are happening during evaporation. So if you have evaporation of water from the sea surface, from the ocean, it's very important whether this evaporation is happening into a wet atmosphere or if it's happening into a dry atmosphere. If it's happening into a wet atmosphere that is already close to saturation in water, then the evaporation will be less, because the evaporation, it will be less than compared with evaporation that is happening into a very dry atmosphere. So if you have a wet atmosphere, let's say 95% relative humidity, and then you have another atmosphere that is, let's say 50% relative humidity, then you will have stronger evaporation in the dry atmosphere than compared with the wet atmosphere. And because you will have stronger evaporation, it will go on for longer. And because of this, the difference between the evaporation rate of hydrogen and the evaporation rate of oxygen will also be higher. And because of this mass difference that I was telling you about, and because of this, you will have a more hydrogen evaporated than oxygen. And then you will get an excess of deuterium. This is the deuterium excess. So you can thus link the excess in moisture to the conditions at the evaporation source. Very, very roughly, if you have a lower d excess in precipitation, that means that that moisture is coming from a drier area. If you have higher deuterium excess, that means that it's coming from a wetter area. Also, when you have rain, let's say you have a rain that is very, very limited in amount. So you have something like, I don't know, 2 millimeters of rain in a very hot day. That means that the raindrop, as it travels through the atmosphere from the cloud base down to the surface of the earth, will also evaporate in the dry air. So that means that it will go through this strong fractionation process. And in this case, the deuterium excess of that raindrop will be much, much lower. It will be something like 2 or 3 or something like this, maybe even close to 0. So again, it is related to relative humidity, because if the humidity of the air as the rainfall is dropping is very, very high, like so it's raining, very small amount of rain, but in a wet atmosphere, close to saturation, basically there will be no evaporation happening to that raindrop. So like this, you can track using the deuterium excess what is happening to the moisture, for instance, during evaporation, whether it's from the ocean or whether it's happening in a dry atmosphere, or if you are in a surface waters like rivers or lakes, these will evaporate. Let's say it's summer, it's hot, it's dry, and there is evaporation. Now, if it's evaporation in dry atmosphere or it's evaporation in a wet atmosphere, the deuterium excess will change. So if you look at only delta O18 and delta 2H, if you evaporate a body of water, you will change the delta O18 in a certain way, regardless of whether it is dry or warm. However, the D excess will be strongly influenced whether it is dry or warm. So for instance, let's say you have how can you practically use this? Suppose that you have you are in a dry day, it rains, and the water will get on the ground. And because it's dry, very dry and very hot, some of that water will evaporate before getting in the underground. So once it will get eventually in the underground, it will carry with it this evaporative signal. So it will be depleted it will have a very low D excess, let's say 2. So now thinking that in the previous few months, let's say, you had no evaporation. That means that the d-excess of the water that is infiltrating is around 10. And then you have a period with extremely low precipitation and very high evaporative conditions. So the d-excess of the water that will infiltrate will be extremely, extremely low. So then if you measure then further in the ground, let's say in the karst spring or in the cave inside, the water that is getting down there, you can track this evaporative signal from the surface to the ground. And then you can, if you do a mass balance as well, you measure the discharge, and then you can say, okay, how much water was coming from this heavily evaporated water, or maybe it was not coming, maybe the spring was not conditions. So you can track the processes from the surface to the underground and better understand what is happening, where is the water coming from, how much water is coming from one period or the other. That would be one of the the possibilities of using stable isotopes. And I said this much also because I saw the other question in the chat, how can we further use these? And this could be one of the possibilities. And then let me quickly show you here. So you see, this is from the first data set from the Rio Bueno data. And you can see here that the sinks and the springs, so this is data from March through May, if I remember well. So you see that the sinks and the springs have more or less similar values. And that you could say, and both of them are lower than that precipitation from the same amount. So that means that neither the springs nor the sinks in March, April 2021 were fed by precipitation that was falling in March and April 21. So that means that this water, in the case of sinks, depends on how long the river is before sinking. It could be that it's coming from a different region, or it could be that it's also having water that rain that came from January or February, which would theoretically would have lower values. And the same is for the sinks, and you can for the springs. You see, so these springs that were collected, the water from the springs that was collected in April and March 2021 is lower than the precipitation in March and April 21, meaning that this water, so the transfer time of the water in the Rio Bueno catchment is more than at least 2 months. It could be 6 months, or it could be more or less, but it shows us that it's not direct precipitation that fell in March and April feeding those springs. And the same is true for rivers. You see here in blue, and you see here the wells, the deep wells in green. So the rivers are carrying an isotopic signal that is more conservative. So the water of the rivers in March, April 2021 was also coming from precipitation that fell before, maybe in January, maybe in February, or it fell in, depending on how long these rivers are, it fell maybe in a different area, higher elevation or so. So this is how the stable composition of precipitation and different water bodies like springs and rivers can be used.
Okay, thanks so much for that very comprehensive response to both questions. Reminder, you can raise your hands if you have any questions, and they will be answered. I have a question. Given the importance you said of having that meteoric waterline, is it possible that if we were to include precipitation values or precipitation results captured for other isotope projects in Jamaica, could that be used to create a local meteoric waterline?
Yes. Yes. And this is a very important, this is an extremely important thing, because it is generally assumed that the meteoric waterline, it's more or less the same for a given region. Mm-hmm. Now, it could be so, or maybe it could be different. And I see Oliver is raising his hand, so maybe he has a comment. So the more data, the better. It can be used, to compare data from different periods to see if the meteoric waterline is the same, or compare data from other projects with similar data from neighboring countries to get a better idea. So yes, I think it's simple and clear and loud. Yes, it's the best answer. So
all right, about Oliver to comment as well.
Yes, hello. Can you hear me?
Yes.
Good. Yeah, I have both a comment and a question. So my comment is that we really need to look at, let's say, the time scales and the timings where in other projects in the area and also in Jamaica, samples have been taken. So I think it's very important to have this long-term observation. And that is something that is a national endeavor that is important for the whole nation and for different hydrological projects, not only for one. So the one thing is for, let's say, our immediate activities, we need to look what type of data are there and from which time. But also, yeah, we in a way, we have like the stewardship to build the foundation also for the future with our project. So to have basically GNIP stations that can be operated on a long time, and that by different Jamaica projects that the agency had already in the past has always been a difficulty. So over the different projects that we have not yet really been able to establish really long precipitation time series, right? So we could have done this already for a few years. So important that we try to do this now, and that this is kind of sustainability, because meteoric waterline, you need at least 3 or 4 years of data, probably. But if meteoric waterline is influenced by rare events, for example, if there is some remote connection to El Nino and the control of these, then of course, obviously you need more than 4 years to also understand the influence of such events that are not happening so much frequently. So that is my comment. And my question to Aurel is, Aurel, you have presented data, isotope data from GNIP from different stations close by, from other islands, and also from the Central American mainland. Can you, at this point in time, comment a bit about from when these data have been? Is this contemporary data? Is this more historical data? Is it both? That's my question.
Historic data. So it is like the data is from before the data that was collected in Jamaica. So Jamaica was collected in 2021, and all this data is before this one. So that's why I like to link your previous comment that I know that there is some data that was available, but I couldn't find it in order to compare. So for instance, that's why, so the data that is being plotted here, so I plotted delta 18 versus delta 2H. I did not plot it on a time series because they are from different periods. So I've tried to do this, but it was basically not making, I wouldn't say it was not making too much sense, but it was not possible to interpret exactly how, I mean, it was so dispersed, it was not possible to link the data sets between them to make sense, to try to say, okay, we have the same variability in different parts of the Caribbean, like, I don't know, Puerto Rico and Honduras, or Havana in Cuba and the Dominican Republic. So it's a lot of gaps in the data, and it would have been like showing some data and then maybe full of question marks. So why is this important? What this data is telling us for our purpose here? So it was not clear at all. So this is why I did not show it, and I think that this is why it is important, to gather, like as you said, this data that exists somewhere, and then try to compare with the similar data from the neighboring regions.
Okay, thank you. I have one final question. I remember collecting the data for Tropical Storm Grace, you're welcome. But when you showed the impact that the one tropical storm had on that August reading, and how that reflected compared to everything else, how much impact then does tropical storms and hurricanes have on meteoric waterline if you're going to try to mitigate against that impact, what it does for the waterline locally and globally?
It changes. So it changes. The slope is more or less the same, so it's around 8, but the intercept now is 12 with the data from the storm is 16.
So that means
it is important. Both it changes also the intercept, but you can see it also in the spring waters and in the surface waters. So all these waters are in August 2021. They were all affected. So all springs, all surface waters, you could see that there was more variability related to the tropical storm Grace than it was in the entire period between March and August, except for the wells. So because these wells were sampling the deep water, I couldn't see any influence. Maybe there was, maybe later, maybe this influence, because these are wells, they are deep wells. Maybe it takes some time to see the signal of tropical storm Grace, but you can see it clearly in the springs, in the sinks, and in the surface, in the rivers.
Okay, interesting. All right, we have one more question from Oliver. That will be the last.
Okay, or a question for the tropical rainstorm Grace and this data. Are you already actively in contact with other people from other places, other islands that have collected this data?
Yeah.
And so I'm currently not in contact, but we should maybe follow up on this.
Mm-hmm.
And question 2, if I look at this comparison, and we have talked before that we want to maybe do a small contribution to a conference or whatever, this already to me looks like a story, and I think we should take opportunity from this just to keep the ball rolling, let's say, in this football game, so that Water Resources Authority with Geoffrey and Aurel, and also from my side, we can maybe join together to bring this also somehow to public. I think that is already a small, little interesting story. Thank you.
Yes. So I know that Ricardo Sanchez Murillo from Costa Rica. So he is collecting. So he's tracking. I was discussing with him, and he's tracking hurricanes, the stables of composition of hurricanes or tropical storms in the wider area. So he's collecting in Costa Rica. He's also collecting in Yucatan and in Cuba. So here, and here. This I know for sure that he is doing, and I know that there is a group that is doing the same in Texas, north of there. I'm not aware of anything similar in Florida or in other parts of the Caribbean. So I think, so I know that he also collected during Tropical Storm Grace in Mexico, but I haven't seen his data, so I don't know his data. And of course, he didn't see the data that Geoffrey collected. So I know that he was collecting at that time, but I haven't seen the data. So definitely he has the data, and yes, also we have it. So, and this is very interesting because it was a direct hit, and we have this hourly data, and with all the climate data that Geoffrey provided, it's a nice story. We can nicely track how a storm was moving through a certain place. So it's not only that you track a storm as it moves. For instance, if you think how a tropical storm was moving, so it moved from the tropics, from the Atlantic Ocean, so it picked up moisture from somewhere here, and then it dumped it here, and it also picked up. So before hitting Mexico, it also picked up moisture from this part, from this area, from this ocean. So the end result here in Yucatan, for instance, or even after it passed Yucatan, it landed on the mainland of Mexico. So it had a history of moisture picked up from here, and then from here. So combining all these data sets, okay, if we have Jamaica here, so we know what was in tropical storm from this basin, And then there is the data in Yucatan, and this is a combination of what was left after it passed Jamaica and what picked up here. And then once further across the Gulf of Mexico and in the Veracruz area in Mexico, then this history of tropical storm hurricanes raised at that time already in Mexico is a combination of moisture picked up from here, moisture picked up from here, moisture picked up from here, and moisture lost here and also lost here on the continent. So there are two ways of looking at this kind of phenomena. One is to track it along the movement as it moves all the way. So let's say where it is. So you can track it, you collect here and then here and then here and then here, and you see how it's changing along the trajectory. Or you can, like Geoffrey did, collect in one spot every hour, and see how it's coming, getting there, and passing you. And then you can have this very nice and clear snapshot of in one spot. You see approaching and leaving. And I guess maybe it's here, like here is the approach, and here is the departure. And here is the tail end, with very low amounts of precipitation. I think you can see here the rainfall amounts are very, very low. So this is in millimeters. So you see the precipitation was increasing, reaching a maximum, and then somehow decreasing in these very, very low values as it left. And if you combine it with the air pressure, you can see the distance from the eye of the tropical storm and so on. And here is the temperature. So it's a beautiful data set, and I think it was very fortunate that we had this.
Perfect timing indeed. One more question from Dr. Gordon Smith in the chat, asking if we've looked at data collected in the previous IAEA studies and how do they compare? Not as yet. I know that we've collated them. I had been collecting some of the data from previous studies back from the one we did in 2013. And I had reached out to you, Debbie, for the stuff from the NIC project. And we're still working with NWC right now on 7004. But I don't think it would be a problem to collate that data and look at it, but that would be further ongoing because we're still collecting data right now. We are planning to collect data for at least another year in the Rio Bueno Basin. We have samples to ship out this month after we collect from March. We should be shipping another set of samples from January to March off to Romania for analysis. And so that would provide more information that we look at for Wednesday, because the other questions I have are for Wednesday. I like what I'm seeing so far with the identification of the signatures for the different sites. And so there are many questions to be brought up from that, which will be done on Wednesday. So if you've been intrigued thus far, please be sure to come back on Wednesday, bring your associates, and have those questions ready for that point in time. I would like to thank Aurel for his very interesting and detailed presentation. I know that we were all enraptured, so to speak. Nobody left the lecture before time. And we look forward to your presence on Wednesday the 16th, again at 9 a.m. when we continue the presentation looking at the application, not just of precipitation, but of the, as introduced, the sinks, the rivers, the springs, the rainfall collectors, and the groundwater sources in the Rio Bueno Basin. Thank you so much for being here, and we wish for you the best for the rest of the day or evening, wherever you may be. Thank you again. Have a great day.
Thank you.